And hi everyone, I'm seeing you guys again today. Okay, so I'm going to talk about how to determine your order of reaction by using graph. Okay, so previously in my previous video, I already talked to you about initial rate method, which is a calculation method to determine the order of reaction. So I give you a few examples, okay, in the notes as well as in the video to guide you as well as to make you practice on how to determine the order of reaction by using that method. Okay, and in the same video, I already told you and explained to you there are another two different methods which include the sketching of graph. Okay, so the first one is the linear graph method and the second one is using Halflives method. Okay, so for first one, I'm going to discuss with you with the linear graph method. Okay, for me, linear graph method is more like a trial and error method. What does it mean with trial and error? That means you cannot fix, okay, or state the order of reaction by simply referring to just one graph. Okay, so that's why if you are using linear graph method, you need to at least plot two different graphs, okay, before you can finally state that this is the order of reaction for that compound or for that reactants. Okay, so what kind of graph that you need to plot for this one? Okay, so it means you have to refer to the integrated rate law formula that you already learned. Okay, luckily here in matrix we're going to focus on zero order, first order and second order. That means your graph will only consisting of either zero order reaction, first order or second order. Okay, so what kind of graph that you need to plot? Okay, let's look at the formula. Okay, so this is the integrated formula. Okay, so in the zero order we have this formula. Okay, and the first order I'm going to refer to this, and the second order I'm going to refer to this one. Okay, for a linear graph, as you learn in mathematics, we must compare the formula that we have here with y equals to mx plus c, as we all know. Okay, so y is for the y-axis, m is for gradient, okay, and x here is referring to x-axis. Okay, what about your c? Okay, so your c is actually your y-intercept. Alright, okay, so let's look at the zero order reaction. Okay, so if it's a zero order reaction, okay, so that means you have to plot a graph of concentration versus time. Okay, so A naught is your C or y-intercept, and your gradient should be a negative k. So this is your gradient. So if you plot graph of concentration versus time and you get a straight line like this with a gradient of k, that means it's a zero order reaction. Okay, but if you don't get a straight line but a different kind of line, or is it a curve, so that means it's not a zero order reaction. Okay, what about if I want to plot a first order reaction? Okay, so I'm going to use this integrated rate law formula with, okay, so this is my y-axis, ln E t, okay, versus time, and your time depends. Okay, if the data given to you is in seconds, so you're going to fix to be used in second. If it's in minute, then fix it into minute, and so on, whatever units for your time is given. Okay, and you should get a straight line here, okay, with a gradient of negative k. Okay, so if you get a straight line, again, this is referring to a first order reaction. Okay, if, okay, you're plotting this one, okay, so for your second order reaction, okay, so your y-axis based on the given formula, it should be 1 over AT, okay, versus time. Again, you must state the unit. Is it second, or is it hour, or is it day, or so on. Okay, as you can see in this one, it's a plus symbol. That means it should be a positive gradient. Okay, so in this one, you should have this kind of graph with like this. Okay, with the gradient K. Okay, if you plot the graph and you can see one of the graph that you plot based on this different formula, okay, if you get a straight line, that means that is for the order of reaction for that reactant. Okay, so I'm going to explain to you with another example, okay, which might be helpful, okay, for you to understand better about this. Okay guys, so let's look at this one example. Okay, so I have here, okay, the decomposition of nitrogen dioxide to form nitrogen monoxide, okay, as in this following chemical equation. Okay, so whenever you have this kind of question, okay, sketching graph, you will be given this data, okay, which including time and concentration, okay, and from that data you're going to manipulate the data, okay, to if you want to plot a graph for first order reaction, so you will need to calculate ln concentration of that reactants, okay, and if you want to plot for a second order reaction, that means if you are referring to the integrated rate law formula, that means your y-axis need to have be 1 over concentration of NO2. So this is for your second order. Okay, so if it's a first order, it's ln concentration of your nitrogen dioxide. So this is first order. Okay, and if it's a zero order, you can just simply continue with nitrogen dioxide concentration. Okay, for you to be safe, okay, so and it makes your life easier, that means you need to first start by calculating all that required information before you proceed with the sketching of the graph, just like what I did here. Okay, so I calculate ln nitrogen dioxide concentration and then 1 over nitrogen dioxide concentration. Bear in mind, okay, this concentration of nitrogen dioxide is not 10, but this one is actually 10 to the times 10 to the power of negative 3 molar. Okay, it's been simplified in the column title, so you need to be alert. Okay, it's just not 10, it's 10 times 10 to the power of negative 3. That means when you're trying to calculate, okay, for the concentration of nitrogen dioxide at 10, okay, so for the first order is ln nitrogen dioxide concentration, that means it become ln 10 times 10 to the power of negative 3. Okay, so you will get negative 4.605. Okay, same goes on with at times 60 seconds. Okay, so it's ln 6.83 times 10 to the power of negative 3 equals to negative 4.986. Please be alert about this scientific notation. Okay, sometimes they include it in every data, sometimes they just refer at the column title. Okay, so I already plot 3 different graphs, okay, for my zero order reaction, first order reaction, and second order reaction based on this experimental data. So let's look at each graph. Okay, so these are the 3 graphs that I obtained, okay, from the experimental data. So the first one here, okay, so this is my zero order reaction because I plot graph of concentration versus time, so that one is for zero order reaction. Okay, the second one, okay, with the orange plot, this is for my first order reaction, okay, which is graph of ln nitrogen dioxide concentration versus time. Okay, and the third one is based on the concept of second order reaction, which I plot graph of 1 over nitrogen dioxide concentration in the unit of per molar, okay, versus time. As you can see, between these 3 different graphs, only this third graph shows a linear graph, a straight line, okay, a straight line here. This is considered as a straight line, whereas the other one, this one is like a curve, and the zero order concentration, zero order reaction is definitely a curve. Okay, so I can state that the decompositions of my nitrogen dioxide to oxygen and nitrogen monoxide is a second order reaction based on the graph that I already sketched here. Okay, so this linear graph only shows in my second order reaction graph. So therefore, decomposition of my nitrogen dioxide is a second order reaction. Okay, so this is what I tried to say. You need to plot at least more than one graph. Okay, at least two graph is compulsory. For example, if this one I plot as first order and second order, and I found out that it shows a linear graph in my second order reaction, so it's a second order reaction, then I can make a conclusion that my nitrogen dioxide decomposed at the second order reaction. Okay, if these two different graphs does not show any linear graph or straight line, that means the other one graph that you did not plot is the order of the reaction. Okay, I hope it's already clear to you. How does we determine the order of reaction by using linear graph method? Okay, so let's write a statement. Okay, based on the graph plot, decomposition of NO2 is a second order reaction because a plot of 1 over NO2 concentration versus time give a straight line. Okay guys, so besides linear graph method, you have another kind of graph to determine your order of reaction, which is known as Halflives method. This Halflives method requires you to plot a graph of concentration versus time, and from that graph, you need to identify the value of first half-life, okay, second half-life, and third half-life. Okay, so from there, you're going to compare these three different values. Does the half-life remain constant from the first, second, and third? Or does the value of the half-life keep increasing or keep decreasing? So from there, you're going to state either the reaction is first order or second order or zero order. Okay, so what is half-life? So half-life is the time taken. Okay, is the time taken for the concentration of reactant. For example, I have compound A as my reactant to reduce by half of its original concentration. Okay, so let's say I have my concentration to be initially 100. Okay, and then it reduced to 50%, and then it reduced to 25%. So 50% is half from the 100 concentration. So this is my first T half. Okay, and when it reduced from 50% to 25%, this is my second T half. Okay, so and then I'm going to compare either this value constant or increasing or decreasing to state either my reaction is the first, zero, or second order. Okay, so for this one, you're going to be given the same type of experimental data, which only consists of time as well as concentration. Okay, so let's first understand what will happen if it's a zero order reaction. Your half-life is directly proportional with the concentration of your reactants. Okay, that means if your concentration continue to decrease, your half-life will decrease as well. So if you have a three different value of half-life, that means your first T half will be greater than your second T half and the third T half. Okay, so that is for your zero order reaction. Okay, if it's a first order reaction, okay, so your half-life is constant. Okay, half-life constant. So that means, okay, either it's a first half-life or second half-life or third half-life, the value remains unchanged. Alright, so this is for your first order reaction. Okay, what about if it's a second order? So If it's a second order reaction, your half-life is inversely proportional with the concentration. That means, okay, decreasing concentration, your half-life will increase. Increase your concentration, your half-life will decrease. So if my first half-life, it will be smaller than my second half-life, as well as it will be smaller than my third half-life. Okay, so this one you need to be remembered in your mind so that it will guide you to determine the order of reaction from the sketch of concentration versus time. Okay, so from this experimental data, I already plot a graph of concentration versus time. Okay, so this is my graph. Okay, so let's discover either this thermal decomposition is a zero order, first order, or second order. Okay, so my original concentration is 10. So this is the original concentration of my reactant. Okay, so when it reduced by half, it means the 10 will reduce by half. 10 divided by 2, it will become 5. So 5 is somewhere here. So this is 5. So that means I need to draw a straight line, and from here I'm going to determine what is my first half-life. So it's from here to here. This is my first half-life. So the gap here is 130 seconds. Okay, let's find out the second half-life. Okay, so from 5, it's going to reduce to 2.5. Okay, so 2.5 is roughly around here. So this is around 2.5. Okay, so this 2.5 concentration. Okay, so this is from here to here is your second half-life. So from 130 seconds to 330 seconds. So the gap here is about 200 seconds. Okay, so your first half-life is 130 seconds, and your second half-life, okay, it's 200 seconds. So what you can see, your first half-life is smaller than your second half-life. So if you are referring to my notes here, okay, so if the first half-life is smaller than the second half-life, that means the reaction is a second order reaction. So we determine the thermal decompositions of our nitrogen dioxide is a second order reaction, exactly that like what we have determined using the linear graph method before. Okay, so it's simple, isn't it? Usually in the exam they will state what kind of graph they are expecting from you, but if let's say they just give you this kind of data, time and concentration, and you need to plot a graph, okay, so you can choose either to use linear graph method or graph of concentration versus time in the half-life method, whichever that is simpler and easier for you to score. Okay, don't forget to try the questions that I give to you through your Google Classroom. Bye.